So in the last class we have discussed about the second objective, which was to distinguish between the crystalline solid and amorphous solid. Okay, but here our third objective is to actually understand, or actually we will going to mainly classify the crystalline solid only. Okay, so that means we are just now going to concentrate on the crystalline solid. Okay, so basically we have many solids around us, no? They may be amorphous solid, or they may be crystalline solid, but the most of the solid substances are crystalline in nature, mainly all metallic. So all the metallic elements, okay, all the metallic elements like iron, okay, iron, copper, okay, silver, okay, so they will going to exhibit metallic nature. So similarly, there are some also non-metallic elements are also there, like sulfur. Okay, so non-metallic non-metallic elements are also there, okay, like sulfur, phosphorus, okay, iodine, and the compounds like some salts, like compounds. So these are actually elements, okay, all metal elements actually, okay, all metal elements are here also elements, okay, elements. But in case of compounds also, like sodium chloride, zinc sulfide, ammonium chloride, naphthalene, okay, potassium chloride, there are many huge amount of actually solids are here, actually, which exhibits the crystalline in nature, okay, or which exhibit the crystalline properties, okay. So here, for in case of compound, examples are sodium chloride, you know ammonium chloride, potassium chloride, okay, sodium hydroxide, zinc sulfide, naphthalene, or that means they all will going to one they will going to exhibit the crystal nature. So that means what, since there are many, huge amount of crystalline solids are observed in the nature, so actually we have to differentiate, or we have to divide them, or we have to classify them into some subdivision, okay, to understand them properly, because it is not possible to study each and every solid, okay. If we will classify them in some subdivision or subclasses, then of solids, then that subclass will going to exhibit some similar properties, okay. So by studying only one solids from their solids, we can have the idea about the other solid which are also in that subsolid, understand? So that's why we want to divide them, or we want to classify the crystalline solids into some uh, classes or some types, okay. So mainly in this in this chapter we're going to classify this crystalline solid on the basis of the intermolecular force. So on the basis of intermolecular intermolecular forces. So intermolecular forces means, we already know that uh, in a crystalline solid there are some constituent particle will be there, no? Constituent particle will going to form that ordered arrangement, no? But here the constituent particle may be molecule, maybe ions, or maybe what, maybe your uh, even atoms, okay. So but here the thing is that what will be the intermolecular forces. That means here in a solid there will be the solid will be composed of what, mainly molecules, na molecules, they will composed of molecules. Let's suppose the solid will be composed of molecule, or maybe ions, or maybe atoms, okay. So what is the force between that molecules which are in that solid, or what is the force between that atoms which are from that solid, or what is the force between that ions which will going to form that solid. So depending upon the intermolecular, that means inter means what, in between the molecules. Okay, so intermolecular forces. Okay, so the forces which is going to be there in between what, molecules, or in between some the constituent particles. Okay, so what is the intermolecular actually forces which will going to bind them together to form that solids. Okay, so on the basis of this forces we're going to divide the all crystalline solids. Okay, see, here we are only discussing about crystalline solid, okay, not amorphous solid. Okay, so remember this point. Here we are going to divide only the crystalline solid on the basis of intermolecular force of attractions. Okay, on the basis of intermolecular forces we will going to divide them into mainly four categories. Okay, four categories four categories or four types are there. Okay, so they are actually, number one is it one is your molecular 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 uh, second one is your ionic. Okay, third one is metallic, and fourth one is your covalent covalent solid. Okay, so these are actually what, these are actually all are what, all are crystalline solid. Okay, all are crystalline solid. Okay, so these four subclasses are actually, four categories are of what, actually crystalline solid. Okay, we actually classify the crystalline solid into four classes on the basis of, the basis is what, basis is intermolecular force of attractions. Let us now discuss about the first categories of the crystalline solid, which is the molecular solid. Okay, so here you see the name is what, molecular solids. So by actually using this name we can define the crystalline solid. Okay, so that means we know that in case of crystalline solid, the constituent particles will going to give a ordered arrangement. Okay, let's suppose this is the that ordered arrangement. Okay, so here in case of molecular solids, the constituent particles, so here these are the constituent particle. Okay, so the constituent particles will be molecules. Okay, so that means this is one molecule, this is the one molecule, so same molecule. Okay, this is, let's up, if it is hydrogen, that this is hydrogen, this is hydrogen, that means this is hydrogen. Okay, so same molecules, all the particles or the constituents are the same molecules. So if, so what we can say, in we can define the molecular solid as like this. Okay, if the constituent particle of a crystalline solid is made of molecules, then that solid is known as molecular solids. Okay, here you see this molecule may be anything, na? Maybe any molecules, maybe they may be polar molecules, they may be non-polar molecules, or they may even form some hydrogen bond with the other molecules. Okay, so that's why what we have to do, because the molecule may be different for different molecular solids, so again we have to divide this molecular solid into uh, you know the following categories. Okay, mainly three categories are there. The first category is actually known as the non-polar molecular solids. Okay, so what is non-polar molecular solids? That means we are again further divided, we are going to divide this molecular solids, or we are going to categorize this molecular solids into three main categories. Okay, so the first one is actually non-polar molecular solids. Okay, non-polar molecular solids. Okay, so here in case of non-polar molecular solids, that means the molecules will be what, non-polar. Okay, that means the molecules which will going to form that crystalline solid will be non-polar in case of non-polar molecular solids. Okay, but the thing is, do you know do you know what is polar or what is non-polar? Do you have any idea about the polarity or non-polar molecules? So let's suppose we have this HCl molecule. Okay, so this is a molecule. Okay, and hydrogen molecule. Let's suppose this is a HCl molecule, this is a hydrogen molecule. So can you tell me which one will going to exhibit the polar nature or which one will going to exhibit non-polar nature? Can you? Yes, you see, actually we know that this bond, okay, this bond is what? Covalent bond. Na? Why covalent? Because one electron will coming from hydrogen and one electron will going to donated from the chloride, and these two electron will going to share between what? Hydrogen and chloride to form that bond. And we know that in case of covalent bond, the electrons will going to be shared between the constituent atoms. Okay, so that's why this bond is what? This bond is your covalent bond. Okay, covalent bond. And similarly, this one also, one electron will come from this hydrogen and the other electron will come from this hydrogen, and they will going to form this covalent bond. Okay, covalent bond, because they will going to share these two electrons. Okay, so the thing is that here again, please remember this point, that the polarity, that means whether a molecule will going to give you know, that polar nature or non-polar nature, it is actually only, you know, covalent bond will going to exhibit these properties. Okay, polar and non-polar nature. Okay, so here again, if you concentrate on this molecule, then you able to notice that the electronegativity of chloride is higher than the electronegativity of hydrogen. Okay, so that means these electron pairs, okay, so this electron pairs is actually this electron pair is shared by between this hydrogen and chloride, na? Clear? But the thing is that since the chloride electronegativity is higher than hydrogen, that means chloride will going to pull these electron pairs more towards the chlorine. Okay, okay, so that means the electron will be no longer at this position, the electron pair will be at this position. As a result, the electron environment will be shift more towards the chloride. Electron cloud will be shift towards chloride. That means chlorine. Okay, so it will become del negative. Okay, understand? And it should become del positive. Because why del positive? Because the electron cloud will going to move from this position to this position, from left positions to right position. That means from hydrogen to chloride. So this is become positive, del positive, and this become del negative. But in this case, the electronegativity of this hydrogen and this hydrogen is same, so that the electron pair will be remain at the center of this bond. Okay, understand? So that means the electron pair will be at the center, so no polarity will be there. Understand? Clear? So that means this one will be your polar bond, or this molecule will going to exhibit the polar nature, and this will going to exhibit what? Non-polar nature. Or that means what we can say, this is a non-polar molecule and this is a polar molecule. Okay, so that means if hydrogens will going to form the crystal, okay, that means in this constituent particles, let's suppose here hydrogen is present, here also hydrogen, 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 here hydrogen, 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 then this crystal will be what? Then this crystal will be your non-polar molecular solid. Understand? And if the you know, if HCl is here, then it will be what? Polar molecular solids. Okay, and now the interesting thing is that we are dividing the solids, that means crystalline solid, on the basis of what? The intermolecular force of attractions. Okay, so we have actually divided this all the crystalline molecules on the basis of the intermolecular force of attraction. That means the force which will going to bind these molecules. Okay, these molecules with this. Okay, so this molecule, the intermolecular force of attraction of this between this one and this one. Understand? So here, what about the what about the force between this one and this one and this one and this one in case of non-polar molecular solid? In case of non-polar molecular solid, the intermolecular force of attraction is actually London dispersion force. Okay, so actually this London dispersion force is observed in case of non-polar molecules. Okay, that means the molecules which will going to exhibit non-polar nature. Okay, so let us discuss by using a simple molecule which is hydrogen. Okay, let's suppose there are two hydrogens are there. Okay, so here this one is one hydrogen. Okay, so hydrogen means they will have, let's suppose they are positive. Let's suppose only in case of hydrogen, then there will be some electron. Okay, there will be one electron will be there on the in the orbital of this one. Okay, and let's suppose this is another hydrogen. Okay, same, the orbital should be same. Okay, it should be like this one. Okay, positive, this one should be like this. Okay, I can't draw. Okay, so the shape of this actually the sphere should be same. Okay, try to draw properly. Okay, so here it is one electron. Let's suppose this is one electron. Okay, so let's suppose when this one is not here. Okay, this one is not here. Let's suppose this one is not here. Okay, so if this one is not here, only this one is present, then it will have the spherical shape. Okay, the electron will going to we can find the electron in this sphere. Okay, the probability we can the probability of finding the electron is in this sphere. Okay, so when this, let's suppose this hydrogen will go this direction. Okay, so when this will go to this direction, then let's suppose here one hydrogen is there. Okay, then it will going to actually this electron will going to repel this electron, because electron is what, this electron is negative, this electron is also negative, so this will, there will be some repulsion force. Okay, and this electron go towards this direction. Okay, no longer it will be here, it will go towards this direction. Okay, so it will be, the probability of finding the electron will be like this one, because there will be some attraction between the positive and negative, and there will be some repulsion between this one and this one. Okay, clear? So as a result, what will going to happen, there will be a net, it will be what, you see, this will become positive. Now this part, this is a molecule, na? Hydrogen molecule, this is one hydrogen, this is one hydrogen, this is one hydrogen molecule. Okay, so that means this part will become what, del, like del positive, and this part become del negative, because electron cloud is more towards this side. Now clear? So that means there will be a partial charge distribution will be there. That means the partial dipole moment will be observed in these molecules for a little time. Okay, for a very short time. Okay, so this time, since it will going to exhibit, or it will going to have this dipole nature for a short time, then they will going to act as a dipole. So we know that if this dipole will going to be close with some other dipole, let's suppose this is your negative, this is your positive. Okay, then there will be interaction, or there will be some attraction between this dipole and this dipole and this dipole and this dipole. Understand? Or it may be like this, let's suppose this is your del positive, this is del negative. Okay, so there will be some other molecules which have del negative, del positive, then there will be some attraction force. Okay, actually this force is known as what, London force of, actually London dispersion force. Okay, so and this is actually exhibited by what, these molecules are what, non-polar molecules. Okay, so non-polar molecule will going to exhibit dispersion, or what, London dispersion force, or what we can say in other words, we can say that the non-polar molecules will going to bind with each other by London dispersion force. Okay, so that means in this case, in case of this non-polar molecular solid, the interaction between the molecules is what, this one will be your London dispersion force. Okay, that means the intermolecular force will be your London dispersion force. That means the non-polar molecules will going to bind with each other by this force to give the crystalline solid. So as for example, can you give me some example of non-polar molecular solids? Hydrogen, this molecule may be hydrogen. Okay, maybe chlorine, maybe iodine. So there may be there maybe you find some difficulties to understand why this is solid, this is a gas, no? So why we are calling them non-polar molecular solids? The reason behind is that actually this is no doubt this is in the form of gas in normal environment. Okay, that means at 25 degrees Celsius and this 1 atmospheric pressure, it will be as a it will be in the form of gas. That means the gaseous state is stable state in this normal condition. Okay, that means at 1 atmosphere pressure and your 25 degrees Celsius. Okay, but the thing is that when we apply, let's suppose we put this hydrogen gas or the chlorine gas inside a cylinder. Okay, and we're going to pressurize this one. Okay, and let's suppose we're going to decrease the temperature of this one, then it will become what? It will become solid. Why? Because phase transition will going to occur. Okay, so if we are actually talking about that solid state, okay, of this hydrogen chloride or iodine. Clear? So I hope you understand the first this categories of the molecular solid, which is your non-polar molecular solid. So let us now discuss about the next categories, which is what? Okay, before going to the next categories, we have to also we have to know about their physical properties of the non-polar molecular solids. Okay, so these solids are actually soft. Why soft? Because the interaction is very small. Okay, because this London dispersion force, this is actually very the magnitude of London dispersion force is very small. That means the attraction force between these molecules are small. Okay, so if it is small, then what happens? They can break easily. If they can break easily, then this is soft. Okay, that means the solid will be soft in nature. Okay, and they are non-conductor of electricity because there are no any electrons here, na? No free electrons is here, okay, to conduct electricity. And they have low melting point. Same thing, melting point is actually depends upon the strength of this bond. Okay, this intermolecular force of attraction. If the intermolecular force of attractions are small, then it will melt easily. That means we can break this bond or we can separate these molecules. Okay, if the distance actually solid and liquids are depends upon what the state. This state is depends upon the distance between these molecules. Okay, the constituent molecules. If the distance between the constituent molecules are very near to each other, then it will be solid. If they are slightly far from each other, then it will be liquid. And if they are very far from each other, then it is your your gas. Okay, so that's why the melting point of this one is also very small, because the attraction between these molecules in these molecules are small, because the London force of actually London dispersion force is very small. Actually it is not a strong force. Okay, clear? So the properties will be what? The properties will be, the first one is your that these solids are soft. Okay, these solids are soft in nature. And second one is your, they are non-conductor of electricity. Third one is what? Third one is your, they have low melting point and usually in liquid or gaseous state at room temperature and pressure. Okay, so this is all about your non-polar molecular solids. Now let us discuss about the second categories of molecular solid, which is your polar molecular solids. So I'm not going to going to discuss in details, because we have already discussed details about non-polar molecular solids. And but in this case, what will be happen? The molecules or the constituent particle will be actually the constituent. Let's suppose this is your crystalline solid. If the constituent particles is your polar molecules, then this solid is known as one polar molecular solids. Can you give me some example like HCl? Okay, HCl, sulfur dioxide. Okay, sulfur dioxides, this will going to exhibit, or this is actually examples of polar molecular solids. Okay, so and the force between this between these molecules is actually dipole interactions. Because you see in case of HCl, see here, the because of the the electronegativity difference, this will be del negative and this will be del positive. We have already discussed this one, no? So similarly, if let's suppose this is your one molecule. Okay, that means this molecule, let's suppose this molecule, and let's suppose in this case of, let's suppose this molecule this molecule, let's suppose this one is your Cl H, del negative, del positive. So they will be attracted, sorry, this one is positive and this is del negative Cl. Okay, it should be like this. Okay, HCl, HCl. Okay, so this is your del positive, del negative, del positive, del negative. Okay, so this is one molecule. Okay, this is one molecules. Okay, so they will going to, there are many molecules are there in that solid. Okay, so let's suppose we are only considering about these two molecules. Okay, so these two molecules are, let's suppose this one. Okay, so here you see this will going to del negative, this is actually del negative and this is del positive. So these are what, dipole. So there will be some attraction between this dipole and this attraction force, or this force is known as actually dipole interaction, or you can say attraction, dipole attraction, or dipole interaction. That means the polar molecular solid, in case of polar molecular solids, the interaction force, that means the intermolecular force of attraction is what, dipole interactions. Coming to the example of polar molecular solid, actually solid sulfur dioxide solid. Okay, but they are in gaseous form in room temperature. Okay, because at room temperature the stable form of sulfur dioxide is gas. Okay, so solid sulfur dioxide is an example of your polar molecular solid, and the second one is your solid ammonia. Okay, these are actually two examples of your polar molecular solid. Since we know that the physical properties of that solid will be depends upon the actually the interaction force, na? That means the intermolecular force of attraction between the constituent molecules. So in this case, actually in case of the polar molecular solids, the interaction force is what, the intermolecular force of attractions are what, dipole interaction. Okay, interaction, dipole interaction, and the dipole interaction is actually slightly higher than the London force of interaction. Okay, so it is actually stronger than London force of interaction. That means the bone, that means the attraction force between these molecules is higher than the non-polar molecular solids. Okay, so but this is not so strong. Okay, so actually the physical, if you go to the physical properties of the polar molecules, then also these molecules also exhibit the softness. Or that means this solids are soft in nature and they are non-conductor. Second point is non-conductor because there is no any free electrons to conduct electricity. Third point is the melting point, and melting points are slightly higher than actually those of the non-polar molecules, because the bond strength of polar molecules is stronger than, that means not bond, actually the intermolecular force of attraction is higher than the non-polar molecules. Okay, why? Because in non-polar molecules it is London force of interaction. Okay, so in case of polar molecules, so dipole interaction. Okay, interaction, dipole interaction. Okay, the attraction between the constituent molecules. Okay, and in case of your this is what, for polar molecular solid. Okay, but in case of your non-polar molecular solid, in case of non-polar molecular solid, the force will be what, London force. Okay, London force of attraction. Okay, and the London force of attraction is actually lower than the dipole interaction. That means the strength of the London force of interaction is actually not so high, not actually the in dipole interaction is strength is higher than London force of attraction. So that means this bond is stronger, that means this interaction is stronger than these interactions. Okay, so to break this interaction or to separate these molecules, we have to apply more energy. Okay, that's why the melting point of polar molecular solid is higher than the non-polar molecular solid. So the last categories of molecular solid is hydrogen bonded molecular solids. Okay, but here in this case the constituent particles will be actually molecules. Okay, the first of all they must actually the constituent particle must exhibit the ordered arrangement, because they are in crystal, okay, crystal in nature. So they must exhibit the ordered arrangement. Okay, first of all, this is the first condition. And the second condition is that in case of hydrogen bonded molecular solids, the constituent particle must be made of molecules. Okay, that means these constituent particles are the molecules. Okay, but that molecules must have a hydrogen which is bonded with maybe fluoride, maybe oxygen, maybe nitrogen. Okay, that means the molecules, let's suppose this molecule must have this uh, any one of these three bond. Okay, anyone, maybe this bond may be present, maybe this one, or maybe this one. Okay, so let's suppose let's take an example. So in case of water, okay, in case of water is 2. So water will be what? This one is the structure of the water molecule, no? So this is the molecule. So that means if this molecule, that means this water molecule is here, that means the constituent particles, or the constituent if the constituent particle is your water molecule, okay, suppose that means this part is what? Water, 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 here also water, water, water. Okay, so if the constituent particle is your water molecules, and here you see, here this is the water, okay, and in the molecule of water we have one oxygen and hydrogen bonds. So see here in between these three it is present, na? OS is present, that means this one is present. Okay, this bond is present, that means this molecule, if this water molecule will going to form that molecular solid, then that molecular solid will be your hydrogen bonded molecular solids. So how they will going to form that hydrogen bonded molecular solid? So let us discuss about this. Okay, so first of all, what is the condition? The condition is that the constituent particle must have a molecule which must have what? Any one of these three bond. Clear? So hydrogen bonded molecular solid can be defined as like this. Okay, the hydrogen bonded molecular solids are those crystalline solids in which the constituent particles are made of some molecules. Okay, and the molecules must have a bond amongst them. So that means amongst them one bond must be present in that molecule, that means in that constituent particles. Understand? So let's suppose this, in case of this is the example now, water. So let's now discuss about this how they will going to form the hydrogen bonded. Let us discuss this one. Okay, so let's suppose this is your oxygen. Okay, oxygen, hydrogen, hydrogen. Okay, so this is your oxygen. Okay, this is your hydrogen. Suppose this is your hydrogen. Okay, so this is one molecules and this is the other molecule. That means this will going to represent this molecule, and this will going to represent this molecule. Okay, so here you see, since there are some dipole moment, no? Negative, this is positive, and this is positive, this is positive, this is positive, this is negative. Okay, so here this oxygen and this hydrogen will going to form a hydrogen bond, intermolecular hydrogen bond. Okay, so from the above discussion we have understood that the intermolecular force of attraction between the molecules, the constituent molecules in the hydrogen bonded molecular solids are what? Intermolecular hydrogen bond. Okay, but here the thing is that the intermolecular hydrogen bond is stronger than the dipole-dipole interaction, and also the London's force of dispersion. Okay, so that's why the stronger hydrogen bonding actually bind these molecules of such solid like water. Okay, which is actually ice. Okay, they are and the physical property, coming to the physical properties, they are non-conductor of electricity, because there are no any electrons, free electrons are there, no, available to conduct the electricity, and generally they are volatile liquids, and also they are soft solid. Okay, because the interaction actually this this interaction is not so strong. Okay, they are strong, no doubt they are strong, or they are stronger than dipole-dipole interaction and the London force of interaction, but this is not the not so strong, that so that's why they are soft solid under room temperature and the normal pressure, that means 1 atmospheric pressure. So we have discussed about the first categories of crystalline solids, which is your molecular solids, and also we have discussed about their subcategories, which are actually subcategories of what? Subcategories of your molecular solids, which are non-polar molecular solids, polar molecular solids, and hydrogen bonded molecular solids. Okay, now coming to the next categories, which is your next categories of your crystalline solid, which is ionic solids. Okay, so here the name is what? Ionic solid. That means the constituent particles will be what? Ionic in nature. Okay, so that means ions are the constituent particles in the ionic solids. Okay, so as per example, we can take an example of, let's suppose, sodium chloride. Okay, sodium chloride. So actually sodium chloride are actually sodium positive and Cl negative. Okay, so these constituent particles are actually, one particle will be your sodium positive, one will be chloride negative, again sodium positive, chloride negative, this is sodium na, so this is chloride. It will be like this one, you see, sodium positive, chloride negative, again this one is sodium positive, chloride negative, chloride negative. Okay, so here this is only I'm just drawing in two dimensional. Okay, but here it is actually three-dimensional structure there actually. Okay, so they are actually three-dimensional arrangement. So above it, actually above the sodium, also here there one chloride will be there, and the below the plane actually one chloride will be there, and upside here one chloride, and here also chloride will be there. That means one sodium will be surrounded by total 1 2 3 4 5 6, total 6 chloride. And okay, understand. So here if you notice this one, here actually this one is what? Positive, and this one is negative. Okay, so they are actually ionic form now, so that's why this is known as ionic solid. Okay, so here the force, the intermolecular force will be what? So from the physics we know that if two charges are there, let's suppose one positive charge, one negative charge is there, and the interaction between this positive and negative charge will be actually we can calculate the force of this attraction, okay, by using Coulomb's theory. Okay, and then Coulomb theory, according to Coulomb theory, is the force will be what? F is equal to q1 into q2 divided by 4 pi epsilon naught r square, if the epsilon is your the dielectric medium. Okay, dielectric of this medium. Okay, in which actually these ions are present. Okay, so here q1 represent the charge of this positive charge, and this q2 represent this negative charge. Okay, so this is the force of attraction. Okay, so this is actually the force, intermolecular force, which will be going to actually observe between these two charges. Okay, so that's why actually it will, that means this attraction force will going to depends upon what? The distance between these the two ions, and also the dielectric of this medium, okay, in which the molecules are present. Okay, so one more interesting thing is that this actually Coulombic force of interaction, that means this the intermolecular force of attraction, which is actually Coulombic force na, here in case of ions, and this is stronger than your intermolecular hydrogen bonding and dipole interaction and London force of interaction. Okay, so that's why it will going to show some physical properties, like these solids are actually hard and brittle in nature. Why? Because the intermolecular force of attractions are very high. Okay, this attraction actually, so there will be some attraction between this, so Coulombic attraction. Okay, so this attraction actually is very high na? So that's why these solids are hard in nature. Okay, they will going to so actually they are brittle in nature, and also they have high melting point and boiling points, because they have the intermolecular force of attractions are very high. So to break the intermolecular force of attraction, or to separate these ions from each other, we have to apply more energy. So that's why the melting point and boiling points are high. Okay, since the ions are not free to move, since these ions are not free, no, they cannot move freely. We already know this one, no? This constituent particle cannot move freely in solid state. Okay, so they will not going to conduct electricity, even though they are ion. Okay, this is a very important point. We have already discussed this one, that this constituent particle cannot move freely in a solid state. Okay, so here this ion will not going to actually give electrical, that means this will not going to conduct electricity, these solids, ionic solids. But the thing is that when we mold this one, that means if we melt this one in the molten state actually of this solid, they can conduct electricity. Or when we are going to dissolve this ions, sodium chloride, in water, okay, then what will going to happen? Because in case of water, let's suppose we are going to dissolve sodium chloride, that means this solid crystal in water, let's suppose in water, then what will going to happen? In the water, dielectric constant of water is almost 80. Okay, so that means this one is very high. Okay, if this is very high, then force will be very small. That means this coulombic force of interaction will become smaller. That means this force will become smaller in water medium. Okay, so if it is smaller, then what will going to happen? They can break. That means this molecule going to be far from each other. So that means there will be no any intermolecular force of attraction. There will be, but the intermolecular force of attraction will be small. Okay, that's why they can dissociate it into their ions. Okay, they can dissociate it into their ions. When we add sodium chloride in water, they will going to dissociate it into their respective ions. That means sodium positive and chloride negatives, and this they are free to move now. So that's why they will going to conduct electricity. That means a glass of sodium chloride solution can conduct electricity. Okay, that's why all salt will going to conduct electricity in their aqueous solution. Okay, understand? So in next class we will going to discuss about the metallic solid and the covalent or network network solids. Okay.